Okay, so this is section 8.3, and this deals with scheduling and priority lists. A priority list is a list of all of the tasks prioritized in an order that we prefer. So this has nothing to do with anything but preference right now. And that preference is in the order that we want to execute these tasks. And it says here, if task X is ahead of task Y on the priority list, then it gets priority. And that means that if we are able to, we choose to do X first. However, remember in the previous lesson that not all tasks are ready to go. Some of them have precedence relations that need to be completed. So if that's the case, we skip over a task. Here we go. We skip over it if it's not ready to go. And then we go to the next item in the list and we schedule that. And then we keep coming back to see when X is ready to go. The number of priority lists that are possible is the number of tasks, m factorial. So m factorial, where m equals number of tasks. Oh, that did not. Good. All right. So if we had 4 tasks, that means there would be 4 times 3 times 2 times 1, which is 24 possible priority lists. Okay, so here we have an example. It's called preparing for launch. And we see that we have this little graph here. This is our digraph that represents the tasks and the order they must be completed. It says immediately preceding a launch of a satellite into space, last-minute systems checks need to be performed by the onboard computers, and it is important to complete these system checks as quickly as possible for both cost and safety reasons. Suppose that there are 5 system checks required, and those are tasks A, B, C, D, and E listed here with the numbers in parentheses representing the hours it takes one computer to perform that system check. In addition, there are precedence relations, so D cannot be started until both A and B have been finished. We see that in the graph here, D cannot be started until both A and B are finished. And E cannot be started until C is finished. So E cannot be started until C is complete. The project digraph is shown here. We're marking up the image. Let's assume that there are 2 identical computers on board. We will call them P1 and P2, representing processor 1 and processor 2, that will carry out the individual system checks. How do we use the priority list model to create a schedule for these 2 processors? For starters, we will need a priority list. Suppose that priority list is given by listing the systems checks in alphabetical order. So now we're going to create our first schedule. So here's the priority list, and we're saying that this is given to us. We're not creating the list, it's given to us. Creating the list will be later in the chapter. We have 2 processors, P1 and P2. First in the list is A6. So we say, can we schedule A6? In order to determine that, we have to look at the project digraph. And we see that A6 is connected to start, which means there's nothing holding it back from starting. So we can say processor 1, you're going to do task A. Now this is 0, 1, 2, 3, 4, 5, 6 hours. Since A takes 6 hours, it is going to take all of this block of time for the first computer to go over task A. So you see that we've drawn A inside of this block of 6 hours. We've scheduled it. Great. We go to the next item in the list. Are we able to schedule B right away? And we look and we say, well, here's B, and it's connected to start. So yes, we can do B right away. That's going to be 5 hours. B is done. So these 2 tasks are done. Who's going to get done first? And we say, well, processor 2 is going to be ready right here at hour 5. Next in the list is C, and we say, yes, we can do C, because C is connected to the start vertex, so there's nothing holding us back. Processor 2 is the first one done, so we'll give them task C, which is 7 hours. So 5 plus 7 is 12. 6, 7, 8, 9, 10, 11, 12. That means processor number 2 is going to be busy all the way to the 12th hour of the day doing task C. Great. When processor 1 finishes up, it's ready to go, and the task that is next in line is task D, and we say, well, task D requires both A and B to be finished. And we say at this point here, is both A and B finished? And we say, well, A is done here at the 6th hour, B is done here at the 5th hour. So the answer to that is yes. We can schedule task D. We can put task D right up here after task A. It's going to take 2 hours, so it will be finished by the 8th hour of the day. There's task D. And last is task E. But task E cannot start until C is finished. We see that C does not finish until the 12th hour of the day. And that means that all of this time here is idle time. That means that processor is doing nothing. Once task C finishes, then we can schedule task E, which is 5 hours. 1, 2, 3, 4, 5. There's task E. That means that the whole project will be done at the 17th hour of the day. And now processor 2 will be idle until processor 1 finishes task E. So if we look at this, we say that we have idle time equal to, we have 1, 2, 3, 4 hours that processor 1 was idle, and 1, 2, 3, 4, 5 hours that processor 2 was idle. So that's idle time of 9 hours. That is wasted time. We don't like our equipment to be sitting around for 9 hours. The finish time is 17 hours. And that was our first schedule. So, what are some ways that we can make the schedule better? Well, maybe a different priority list. So we're going to do this same exact problem again, but instead of taking the priority list in alphabetical order, you see that the book gave us the priority list in a different order. And we want to see, well, what does this do to our result? Does it give us a better outcome in the end? So let's work this out again. The first task is E, which is 5. And we say, well, I can't start task E until task C is done. So we go to the next item in the list. Next item in the list is task D. That's all the way over here. We say, well, I can't start task D until both A and B are done. All right. Next in the list is task C. We could start that right away. So let's schedule that. 0, 1, 2, 3, 4, 5, 6, 7. That is the 7 hours that processor 1 will be working on task C. Task C has been scheduled. We come back and we say, can I do task E now? And we say, well, no, I'm looking for what can I start right here at the 0 hour of the day. Task C does not get finished until the 7th hour of the day. Even though it's in the chart, I still cannot schedule task E. I have to skip over it. Next is task D. That requires A and B. We haven't done either of those yet. Task C is scheduled. Now we'll say, well, let's schedule task B. B is 5 hours. Put that in here. Task B will be done at 5 hours. I'm crossing it out because it's been put into the chart. We go back to the beginning and we say, can I schedule task E? We say no, because I need something ready at this time, the 5th hour of the day. Task E cannot be scheduled until C is done, which is at the 7th hour of the day. We skip over E again. We look at D. Can we schedule D? No. We see that D needs A and B to be completed. We skip over D. These next two are crossed out, so we skip down to the last task. Can I schedule A? Yes, it's connected to the start vertex. A is 6 units long. 1, 2, 3, 4, 5, 6. We're going to put A right in here. That's going to take us to the 11th hour of the day. A is in the schedule. Now we go back to the beginning of our list. We say, can I schedule task E right here? Because processor 1 is going to be available first. And we say yes, because in our chart, task E can be done as soon as task C is done. At this point, task C is done. Let's schedule E. It's 5 units of time. 1, 2, 3, 4, 5. There's task E. It's done at the 12th hour of the day. It's scheduled. Task D we can look at. It's the last one. It can be scheduled after A and B are done. Here's task A. Here's task B. They're both done by the 11th hour of the day. I can put D right here. It's 2 hours long. That means this whole project is finished in 13 hours with only 1 hour of idle time. So we see that we did the same exact scheduling problem. If we go back to the previous slide, it took 17 hours and our computer spent 9 hours idle. That was a waste of our equipment's time. If we come back to this slide, the equipment was only idle for 1 hour. We got the whole thing done in 13 hours. So we took off 4 hours off of the total project time. And that is the goal of scheduling. How do we schedule tasks that are dependent on each other through their precedence relations so that we can minimize idle time and efficiently get to the finish time? So we saw that one way to improve efficiency was to change around the priority list, but sometimes there's another way to improve efficiency, and that is introduce a new processor. Now we have 3 processors going. So does it make sense that we can get work done faster with more workers? And we say yes. It's not always the case, but yes, if there's enough work to go around, we can usually get the job done faster if we have more workers. So we go through this process again, this time with 3 workers to give the tasks to. We start with task E. We see that we can't do that because it's waiting on C. So we skip over to D. We see we can't do that because it's waiting for A and B. We skip over to C, and we say, yes, we can schedule C. That's going to be 7 hours, 0. There's the 7th hour. Here's task C. Now at hour 0, we need the next task. So we say B, which is 5 hours. And then at hour 0 with the third processor, we have A, which is 6 hours. So these 3 are in the charts. Now we say which processor is going to be ready first, and we see that processor 2 will be ready first. Can it do E? No, because E cannot start until C is done, and we see that C does not finish until hour 7. Can we do D? And the answer is no, because D cannot be started until both A and B are done, and A and B will both be done at the 6th hour. That means that this is going to be idle time, and then we can say that D can be done with its 2 hours. Now that that's scheduled, E can be done as soon as C is ready, so that's 5 hours we'll add on to here. 8, 9, 10, 11, and 12. So there's E. That means that the rest of this time, the other 2 processors are idle. And if we count all of the blocks of idle time, we see that processor number 2 was idle for 5 hours, and processor number 3 was idle for 6 hours. So we have a total idle time of 11 hours. And the finish time is 12 hours. So if we go back to our previous slide, we see that we shaved off 1 hour by introducing a third processor, but we have much more idle time now. So if getting it done as early as possible is really that important, it would increase cost and get it done faster, but we see that there would be a bunch of downtime. We'd be paying for machinery that would be not get used through the entire time. As a matter of fact, 11 hours and 12 hours, that means almost the entire project time you have a machine doing nothing. Okay, and just to go through our conclusion, in this lesson we learned what a priority list was. We created schedules using priority lists. We identified idle time and finish time from our schedule. And then we explored how different priority lists can produce more efficient schedules. And then we looked at examples with 3 and 2 processors. So your assignment will require all of that of you. The next lesson that we have will introduce us to techniques for creating our own priority lists. For now, priority lists will be given to you, but our goal is to eventually create efficient priority lists of our own.